Oh, sorry, not a number. Okay, let's fix that. A digit.
Yeah. Okay. Yeah. I was gonna.
Yeah, not a number. There's an infinite number of numbers.
Yeah. So I was gonna clarify that.
Yeah, sorry.
Yeah, the number is a single digit number, so 0 through 9.
6,760.
Yes.
8,760.
Oh.
Okay, wow.
It's six.
That's-
Oh, I heard 6,760.
Yeah.
Okay. Yeah, 6,760 is correct.
Yeah.
And this is because if it's made up of a letter and a digit and a letter, there are 26 possibilities for a letter because there's 26 letters. And then there are 10 possibilities for a digit because there's 10 digits, 0 through 9. And then the final letter also has 26 possibilities. Yeah. So you multiply all those together.
Thing. Yeah, one other thing, guys, is that so actually the solution, well, on the next slide for number 3, the solution says 26,500. But we had 25 at the end instead of 26. So we didn't clarify that the letters were going to be different letters. So what you guys did was completely right.
Yeah,
so
that was right. Yeah, the
because
solutions.
the answer on the slide says 6,500, but technically we didn't clarify that the letters were different letters. So you guys got that correct.
Yeah. Okay, one more question. How many phone numbers can be made if the first of the 10 numbers have to be non-zero? And I just included the format of the phone number because, yeah, just because. By the way, you can use a calculator if you really have to.
Yeah. I don't think a calculator is necessary, but
Yeah.
if you need to, then you can.
I think that's
Okay,
right.
well, I don't know how many zeros are there, but
Yeah.
okay.
1, 2, 3. Yeah, that's
1,
right.
2,
That's right.
3, 4, 5, 6, 7, 8, 9. That is right.
Yep, that's the correct answer. Yeah, for this one, again, since the first, normally you would just do 10 times 10 times 10 times 10 times 10 times 10, 10 times 10 to the 10th power. But since the first digit can't be 0, you actually only have 9 possibilities for the first digit. So instead, it would be 9 times 10 to the 9th power, and that would be 9 followed by 9 zeros. So yeah. Here are the solutions. One of them is defective. So yeah. Okay.
Wait, so before we proceed, probability, I just want to ask if anybody has any questions so far. Why would we do 9 times 10? Okay, Amy, you want to explain that?
Sure. Okay, so since a phone number is made up of 10 digits, you would normally have 10 possibilities for each digit. However, the question says that the first of the 10 digits has to be non-zero, which means that it just means it can't be 0. So the first of the 10 digits would, wait, let me get the little pen. Okay, the first of the digits would have from 1 through 9. Oh, okay, yeah. So yeah, first digits would be 1 through 9, but all the others would have to be from 0 through 10. So yeah. Okay.
So does everybody understand? Wait, for number 3, 26 times 10 to 25 is 6,500, right? Yes, so it is 6,500, but wait. I think the question did clarify that there would be a different
shoot,
letter.
yeah.
Okay.
A different letter. Sorry, guys. It is a different letter, not the same. Okay.
Yeah, okay, so the question again, really quickly. So it says it's made up of a letter followed by a number followed by a different letter. So there's 26 possibilities for the first letter, 10 possibilities for a single digit number, and then 25 possibilities for the final letter because it has to be different than the first one. So thank you for clarifying that. Thank you for bringing that up, Bishra. I think, yeah, it is actually 6,500. It is 6,500. For a second there, I didn't read the entire problem, and I thought we didn't clarify that it would be a different letter. Thank you for bringing that up. So yeah, it actually is 6,500 because the problem clearly states followed by a different letter. So
Yeah. Also, Tommy asked, I thought all the digits had to be non-zero. The question said the first of the 10 digits have to be first of the 10 numbers have to be non-zero. So it would just be the first number. The other numbers are fine. Okay, wait, are there any other questions? Okay, all right, so we're gonna now move on to probability. So yeah, Sai, you can do this slide.
all right. So probability is simply the desired outcomes, basically the outcomes we want to calculate for, divided by the total amount of outcomes, or the total number of possibilities for an event.
So let's look at an example. So, well, not example. Basically, probability is, as Sai defined it, is the desired outcomes divided by the total outcomes. However, probability also tells us basically the chances for something to happen, where a value of 1 means that it's 100% likely to happen, and the value of 0 means it's completely impossible, never going to happen ever. And a value of 1/2 means it's in between, it's equally likely to happen or not happen. And probability is always a number between 0 and 1. So for example, what would be something that has a very small probability of happening? You guys can put it in the chat or unmute, preferably.
Drawing an ace 3 times in a deck of cards.
Yeah, that's
That
one.
is pretty low.
That's good. Do you have any others? Anyone?
I have an idea. Okay. Well, yeah.
Oh,
Winning
yeah.
a jackpot. Yeah. I was actually just gonna say winning the lottery seems to have a very, very low chance.
Yeah.
No.
Okay.
And yes, looks like you guys know.
What's something that
What?
is okay, now what is something that has a very high probability of happening?
Getting a heads on a coin.
Yeah.
Yeah, 50%. Getting a red card, being awake. Well,
Yeah. I mean, you should be awake right now. So.
yeah, hopefully, yeah.
Getting anything but a 5 on a dice roll.
Yes, that
Yeah.
has a pretty high probability. I was gonna say not drawing a ace in a deck of cards. A lot of these things have extremely high probabilities unless you sleep all day. Yeah. So yeah, some of the things you guys said have pretty high probabilities. So you guys seem to understand the concept of probability. So with that, I think we can move on to a basic question.
All right. Yeah.
Probably not winning a lottery. Yes. Yeah. So if I have 11 socks in my drawer where 7 are red, 2 are green, 1 is red, and 1 is yellow, what is the probability I draw a red sock?
1/11.
7 or 11. Yep, that's the right answer. So
Oh, shoot.
we're
It
eight
looks
over
like it says 1 is red. That shouldn't be 1 is red. It should be some other color that's not red. So, shoot.
wait, it's fine. It's fine. So you guys seem to actually read the problem. Yeah, you guys actually have like read the problem, which is good, right? So the answer is 8 out of 11. If we considered that 1 red, but it's actually 1 blue instead. So we're really sorry for that. But good job on actually reading the entire problem all the way through. For those of you who said 8 over 11. But for this one, we would just want to find the total desired outcome. So what would the desired possibility be? What would the desired outcome be? 7, right? Yeah. So the desired outcome is that we draw a red sock, right? That's the desired outcome. And there are 7 possibilities for that outcome to happen. So that's 7. But now what are the total outcomes? What are the total possibilities? What is the total? 11, right? So remember what I told you guys. Probability is simply the desired outcome over the total amount of outcomes. So the desired is 7 and the total is 11. So our answer is 7 out of 11.
And I'm just going to quickly interpret what this means because that's pretty important too. a probability of 7/11 in the context of this problem, this means since this value is greater than 1/2, it means that I'm pretty likely going to pull out a red sock. And if you think about it, it makes sense because there's a lot of them in my drawer compared to the other colors. So yeah, basically you don't just like be dividing numbers. Also try to think about like what this actually means. So yeah. Okay. Let's do another problem. Joey likes going to a frog pond, and there's 200 frogs in the pond and 19 are pink. What is the probability that he randomly grabs a pink frog?
Okay, yeah, you guys are very fast. So it is 19/200 because we know that the total desired is 19 and the total is 200. So it's 19/200. Yeah, that's excellent. So good
Pretty
job,
easy,
guys. You guys
pretty
got the
easy.
problem really fast. Yeah, it was a very easy problem as well. So we'll try a couple more.
All right. So there are 4 blue pebbles and 7 red pebbles in box A. And there's 3 blue pebbles and 5 red pebbles in box B. If Charles pulls out a blue pebble from a box, he will win a prize. Which box should he pick the pebble out of to maximize his chances of success? And why should he do that? And if you really need to, you can use a calculator to better compare the probabilities.
Okay.
Yeah, so I'm gonna call him someone. Vishwa, do you want to explain why why you chose box B?
Yeah, so first you have to find the probabilities of both boxes. So for the first box, it would be 4/11 for blue. And for the second box, it would be 3/8. And I just multiplied 4 by 8 and 3 by 11 to get this common denominator. And 33 is greater than 32.
Yeah, that's correct.
Yeah, good job, Vishwa. That's good job. All right. That's exactly how we do it. So the probability is 4 to 7 box A, probability is 3 out of 5 in box B, and 3 out of 5 is greater than 4 out of 7, so the answer is box. So does everybody understand that? No. Okay. I'll explain. So what exactly do you not understand? Tanvi? That I 4 out of 7. Okay. Oh, my bad.
Sai,
Okay, my bad. Yes, okay, I think I made a little mistake. I'm at 4 out of 11. Oh, yeah, I was doing some ratios. All right, I did it in more of a ratiotic method. Okay, so 4 out of 11. I'm sorry, and it's 3 out of 8. So box A is 4 to yes. Okay, I'm really sorry about that. Yeah, it looks like I'm a little too fast there for my own self, but yes. So 4 out of 11 and 3 out of 8. Sorry about that.
yeah.
Okay.
Okay.
That's it. That's that. Okay. So, do you understand that now? I'm sorry about that. Does everybody understand that? Okay, that's great. Also,
All right.
yeah, okay, that's good. And I just wanted to make sure everybody knows like the denominator trick where you cross multiply the denominators to see if a fraction is greater, because that really helps with comparing fractions because it's just much easier to do.
All right. Sai apparently is frustrated with
Oh,
the
wow.
math problem and randomly bashes 3 digits into his calculator. If his answer is supposed to be a 3-digit number, what is the probability that the answer he bashed into his calculator is actually correct? And remember that remember that 0 can't be the first digit of a 3-digit number. So yeah.
Okay, so it looks like we're getting a variety of answers. Okay.
Remember, this is the probability that he gets the right answer. Some of you guys are on the right track.
The probability is actually 1, right? Because Sai obviously gets every single math problem correct. All jokes aside, okay, I'm just joking, obviously. But so I randomly bash in a 3-digit number, right? So the first digit can't be 0. So how many total options do we have for the first digit? Somebody just put it in chat. How many total options? 9, exactly. We have 9. How about the second digit? 10, exactly, 10. And the third digit is also 10, right? So how many total possibilities do we have for the 3-digit number? 900, right? So if I randomly enter a 3-digit number, if I randomly enter a 3-digit number, what like, if I randomly enter a 3-digit number, that would only be a single number, right? So that would be one number. So the total possibility would be what? What would the total probability be? 1 out of 100. That's exactly right. So if I enter a random number, that's only one number, right? So that's one number. But I have 900 total possibilities. So the probability that my number is actually correct is 1 in 900. So that's the correct answer.
Yeah.
All right. So good job, guys. We have one more.
One more. This is a little bit similar to the last problem. Okay, referring to the previous problem, now what is the probability that the difference between Sai's answer and the real answer is less than 5? And by absolute difference, I mean just the positive difference between the two numbers. And I feel like I think I messed up on this problem. Actually, I may want to throw this question out because I realize that this actually has some problems with it.
Wait.
We may need to throw this problem out.
Oh, absolute difference. All right. Yeah. Yeah,
that might
It's
have
fine.
some problems. Okay. If you were to approach, okay, I'm just gonna give you guys the solution, even though this technically is not a good solution. Basically, if you think about it, for a number that Sai, for the correct answer, there will be 9 possible numbers that Sai can bash in, but still like meet this problem's criteria, because if you want the Sai's answer and the real answer to be less than 5, then that means the difference between the real answer and Sai's answer can be either 4, +4, +3, +2, +1, 0, or -1, -2, -3, and -4. So in total, there would be 9 possibilities for what Sai could bash into the calculator, but still like meet the question's criteria. And in total, there are 900 numbers. So in total, the probability would be 1 over 100. However, this actually is not the right answer, but I'm not going to, okay, if you guys want to, I can go into why this isn't the right answer, but.
Well, we can do that. I think yeah, if you want to, I mean, you can just explain, because I mean, some people might be a little confused.
All right, 0 isn't positive or negative. Okay, that's true.
Yeah,
but I'm saying that when absolute difference, it's just like the difference, but the difference can't be negative. Okay, so yeah.
There are some issues with the problem. Like, for example, if I were to choose 100, right? That wouldn't work out, because we know that the correct answer is a 3-digit number. So it couldn't be 90, it couldn't be, So there are a few issues with the problem, but generally, I think we understand the concept, right? I hope everybody understands the concept.
Sorry, by -1, I meant that if you subtract Sai's number from the answer, if Sai's number is greater than the answer, then it would be -1. But we're looking at the absolute difference. So -1 would just become 1. Okay. All right, let's just drop that problem because that might be a little bit confusing. Sai. All right.
Yeah, let's just drop that problem. Let's forget it. Let's pretend that nobody saw it.
Oh wait.
Now we're gonna.
Okay, we have a question. All right. This is the one. All right. So I'm gonna explain problem 2. Okay. So in total, okay, which part of the problem like do you not understand? Like which part of the solution?
Amy, I think you might just want to like, just
Re-explain the whole thing.
do the solution. Yeah, just re-explain the
All
solution.
right. So 3-digit numbers, we have these 3 blanks that are going to represent the digits, right? So because this is a 3-digit number, the first digit can't be 0. So you can have 1, 2, 3, 4, 5, 6, 7, 8, 9 for the first digit, not 0. So you have 9 possibilities for the first digit. Then for the next 2 digits, you have 10 possibilities because these can basically be any digits. So the total number of different 3-digit numbers there are is 900. And this is total. Okay, so then now we want to find like how many ways Sai can get the right answer. Since there's only one right answer, there is only one number that Sai can bash into the calculator and get correct. So this is the desired outcomes. It's just this one, right? So the probability that Sai randomly bashes a number into his calculator and gets it right is 1/900.
How is it 1? I thought you could like put any number for the first digit.
Oh, okay. I see where you're coming from. Basically, this is the total number of 3-digit numbers that are possible. However, this is the number of correct answers that are possible.
Yeah, since there's only one correct answer, right? There's only one way I could possibly get the correct answer. Yeah, 1 is desired. So our desired outcome is 1. That's the correct answer. So our desired outcome is 1.
Oh,
and
okay,
our
I get
total
it.
outcomes is 900. Okay, that's great. Yeah, so if you're ever confused, just relate back to the concept. If you're ever confused on what you're trying to do for a probability question, go back to desired over total. Ask yourself, what is the desired outcome? And then ask yourself, what is the total outcome? And then you have to proceed to calculate the desired and the total. And that's how you solve a probability question. I think we can move on now, right? If everybody is good to go. Are there any questions before I move on? Like on anything? It can be related to anything. Well, anything like A and C. Good to go. All right, thank you. All right, I think if nobody else has a question, well, if nobody has a question, then we can just continue.
Okay. All right, so now we're going to learn about what independent probability is. And as you can tell by the concept number, this is a type of probability. And so what independent probability is the probability of 2 or more events whose outcomes don't affect each other. And so to find like the total probability from 2 or more independent events, we just have to multiply them together. But first, let's brainstorm. What are some events or just things that like don't affect each other? Different outfits. In certain situations, yes. The number of shirts, number of rings, yeah. Coin flipped in a dice roll, yes,
Yep.
that is definitely
So you
independent.
guys know.
Yeah, so basically, you guys gave some examples. Coin flips, dice rolls. Another thing that you guys didn't mention is cards. If you draw one card out of a deck but replace it into the deck immediately afterwards, then if you draw a random card again, those 2 events will be independent because the card deck is in the same state that it was previously. Oh, okay. I just mean like, for example, if you have like a dice roll or coin flip, the outcome of the dice roll won't affect the outcome of the coin flip. So for example, if you roll a 6, that won't affect the probability of getting a heads or tails. That won't make you be more likely to get heads or more likely to get tails. So we would consider those 2 events independent. Okay. So, all right, let's look at an example of an independent event. Sai, you can do this slide.
Okay, so Penny flips a coin 5 times. So what is the probability that she lands 5 heads? So remember, this is independent probabilities.
Yeah. So, okay.
Okay. I'm gonna wait a few minutes for you guys to solve the problem.
Oh, we have some answers.
Okay, yeah, looks like we already have some answers, and most of the answers are right. 1 out of 32, and I'm actually gonna ask one of you guys to explain to me how you guys got the correct answer. So how about Advika? Can you explain how you got 1 out of 32, which is the correct answer, by the way.
So first, when we flip one coin, there's a 1 out of 2 probability. And since we're doing this 5 times, we would do it 1 divided by 2. And then when we flip it a second time, we'd also do 1 divided by 2. So then we would multiply. So in the end, we'd multiply 1 divided by 2 to the power 5.
Which is 32. Exactly. That's exactly how we do it. So that's exactly how she said it, right? So the probability that I get a heads on the first flip is 1/2, second flip 1/2, third flip, and so on, so on, and so on. And the reason that 1/2 doesn't change is because this is independent probability. It doesn't matter if I get a tails on the first flip. There's still a 1/2 chance that I get a heads on the second flip, right? So the outcome of one flip doesn't affect the outcome of another, and that's why it's independent probability. And that's why we get 1/2 to the power of 5, which is 1/32. All right.
Okay, second example. If the chance of rain today is 1/3 and the chance of rain tomorrow is 2/5, what is the probability that it doesn't rain today or tomorrow, assuming that these events are independent? Careful, you're kind of close, but remember that's asking about the probability that it doesn't rain.
Yeah, you guys are close. And actually, this kind of leads us, well, not leads us away. Good.
Oh, okay.
Okay, well, looks
Yeah,
like you're not
we have
getting,
a lot of correct answers, but you guys
Actually,
do need to
I want-
simplify.
you do need to simplify, so that's important.
Yeah. Okay. Yeah, it looks like after the first hiccup, you guys figured it out. Since it's asking about the chance that it doesn't rain, which is the opposite of it raining, we actually have to do 1 minus the probability of it raining. So basically, the chance of rain today is 1/3. Therefore, the chance of rain tomorrow would actually be 1 minus 2/3. Okay, this is a terrible color. There.
You should maybe go for
1
black.
minus 2/3. And the reason why we do 1 minus this is because if you recall, the
Wait,
probability.
I think it's 1/3.
Sorry, 1 minus 1/3. There we go. Okay, 1 minus 1/3. The reason we have to do 1 minus this is because the probability of it raining or not raining is 1, because it has to do one or the other. So if we do 1 minus the probability it rains, then we get the probability of it not raining. And so we can do the same thing for rain tomorrow. And so that's how we get 2/3 probability that it won't rain today and a 3/5 probability that it won't rain tomorrow. And next, what we do to get the probability that it won't rain today or tomorrow is that we multiply them together. Again, this is just because independent probability, remember, independent events, you multiply the probabilities together to get the total probability. Let's see. I see we have a question. If we divide it, does it make it dependent? And if we multiply it, does it make it independent? Let's not look at dependent yet, because we don't exactly divide to make it dependent. It's not like multiply is independent, dependent is divide. It's not like that. It's a little bit different. But just do know that when you have two events that are independent and you want to get the overall probability, you have to multiply them together to get 2/5.
Yeah. So the independent dependent thing isn't operational based. It's just based off of the event that's occurring.
Yeah.
And does everybody know why we multiply like 2/3 times 3/5? Does everybody know why Amy multiplied? Does everybody understand why Amy multiplied? Or do you guys not? If you guys don't understand, can you guys like say something or put something in chat? Kind of. Okay. Amy, do you want to explain why you multiplied 2/3 and multiplied that by 3/5?
Yeah, it actually kind of relates to the fundamental counting principle, which we already explained. Because in the fundamental counting principle, if you have independent events and you want to find the total outcome, you have to multiply them together. And the same thing goes for probabilities. Even though these aren't whole numbers, you still have to you can still multiply them together to get the overall probability. So yeah.
Okay, looks like you guys understand this. Now we can move on to the third example.
Okay, so you can do this.
John flips a coin 100 times in a row, and on his first 99 flips, he goes on a very, very, very unlucky streak and flips tails every single time. What is the probability that John will flip heads on his final toss? Okay, well, you guys are pretty fast at this. Okay, so I see someone put 1/100, and the reason why is, okay, I think you might need to read the problem a little closer. So it's saying that the probability he will flip heads on his final toss. So remember, this is independent probability. So we don't care that John flipped 99 tails in a row. We only care about the probability of the last toss. And that's not going to change based on the other 99 tosses. So it's still going to be 1/2. So do you understand that? All right, that's good. So it kind of sort of was a trick question, not really. It kind of made you want to believe that it would be different than 1/2, but you know, in essence, it's still going to be an independent probability question. And I think we're good on that question. So we're going to go to some independent probability practice. You guys are going to be doing these problems independently. And okay, that kind of, fit, yeah. Okay. So you guys are just gonna be doing these problems by yourselves, and we're gonna be going over those together.
Oh shoot, okay.
It's fine. It's fine. We can put all three on, maybe. Actually, no, we can just do one at a time. I think that's
Okay.
easier.
All right. Okay, first one. What is the probability of first rolling a 4 on a die and then rolling a 5?
Okay, it looks like everybody got 1/36. I'm gonna ask someone to explain. Here, let me just check. Harsh, do you want to explain how you got 1/36? Harsh?
Yeah, so first you roll for there's a magic stance you get that because
Oh, yeah. Audio's a little choppy.
and standing is for number 5. So and then if you multiply 1/6 times 1/6, it equals 1/36.
All right, yeah, that's exactly right. So originally I couldn't hear you, but I got a little better. So yeah, the probability of first rolling the 4 is 1/6. The probability of rolling the 5 is 1/6. We multiply those probabilities together to get 1/36. So that's pretty straightforward. Now we can move on to a second problem.
Okay. There's a 1/3 of chance of it raining today and a 1/4 chance of it raining tomorrow. What is the probability of raining both today and tomorrow?
Okay, well, I think we have a question in the chat. So,
Where?
Okay, well, sorry, not in the chat. I think I got a message. Can you explain number 1 again? All right, so somebody asked me to explain number 1 again, so I'm just gonna do that really quickly. So, what is the probability that I first roll a 4 on the dice, right? Well, we have the desired outcome is rolling a 4, and the total number of outcomes is 6, right? So remember that probability is desired outcomes over total outcomes. So the desired outcome there's one desired outcome and there's 6 total outcomes. So there's a 1/6 probability that I roll a 4 on the first dice. Now going back to the second dice. So the outcome of my first dice does not result does not result in the outcome of the second dice, right? Because it's independent probability. So using the same concept as before, there's a 1/6 probability that I roll a 5 on the second dice. Now going back to the fundamental counting principle, there are in order to find like the total probability of both of these events, I simply multiply their individual probabilities. So that would be 1/6 times 1/6, right? And 1/6 times 1/6 is simply 1/36. So that's how we do number one. I'm sorry I didn't explain it in depth enough. But I was just assuming that most of you guys understood that. But do you guys understand now? Do you understand? Okay. Give me 1 second.
Okay. Yeah. So second problem.
Okay, that's
Oh, okay.
yeah. So yeah, looks like it's being understood. Okay, that's great. Okay, we can wait. Second problem. I think we already had answers for the second
Yeah,
problem.
we had a
right?
lot of answers.
Yeah. So 1/12. Everybody got it right. It's 1/12, and that's a pretty straightforward problem. So we can just move on.
Yeah.
Wait, does anybody
Just
have
in
any questions for number two? I'm assuming it's straightforward because I think we've been over these a couple of times by now. So yeah, 1/12. It's quite straightforward. We can move on to the third problem. Since they're
Okay.
independent, we have to multiply correct. Well, not necessarily, right? Even for dependent probability, we would still have to use the multiplication operation. So it's not really because it's independent. It's mostly because of the fact that we have two different events, and in order to find like the combined like probability of both these events occurring, we multiply, and that just goes back to the fundamental counting principle. So remember the t-shirts thing that Amy was talking about. So if I have a 1/3 chance of it raining today and a 1/4 chance of it raining tomorrow, right? The thing we multiply those together, and because that it kind of relates back to the fundamental counting principle. It's something that you just kind of have to understand. I probably wouldn't do a great job of explaining it. I think Amy would probably do a better job. So Amy, do you want to explain why we multiply?
Again, back to the fundamental counting principle. Whenever you have two different events and you want to find the total, in this case, probability for them, you have to multiply. Yeah. Also,
Well,
why
then
do we add
also,
instead of
yeah.
multiply?
I actually have something to say for this, right?
Yeah.
So if it was, let's say, there's a probability of raining today was 1/2, and the probability of raining tomorrow was 1/2, right? And I wanted to find the probability of running it on both days. If I added, I would get 1, right? Think about that. If I added both of those, I would get 1. Now, that's intuitively that's completely wrong, right? Because if there's a 1/2 probability it rains tomorrow and 1/2 probability it rains today, if I added these, I'd get 1, which basically would say, okay, there's a 100% chance it would rain both today and tomorrow, but we know that that's wrong, right? Because we know it's 1/2. So do you understand? And it would be 1/4 instead, right? Because 1/2 times 1/2 is 1/4. So if we added, we would get a completely wrong answer. So do you understand why we don't add?
Well, at least in this case. Yeah, we do add in some cases, which I'm going to show in dependent probability in a little
Yeah,
bit.
well, yes, of course, yeah, but like an independent probability, well, we actually,
Yeah, in
the operation
independent,
doesn't depend, the operation isn't really related necessarily to the type of probability. It's just rather like what the problem is asking. So that's just, I wanted to state that. We can move on to the third example.
okay, what is the probability of not rolling a 6 on a die and then flipping heads?
Remember the not rolling. You guys have to be a little careful here. All right, well, you guys all right, got it right. So it's 5/12, right? Because the probability that I don't roll a 6 on a die is 5/6. The probability that I flip a heads is 1/2. We just multiply those out and we get 5/12. So that's fairly straightforward. And I think we can move on to dependent probability if nobody has any questions. So if anybody has any questions, can you guys just put them in the chat so we can address those? Because if not, we're just going to move on to dependent probability. So Amy, you want to move on?
Okay. All right, dependent probability. Dependent probability is probability of two or more events that affect each other's outcomes. What I mean is that, like, if the first event ends up being this way, then it affects the second event and makes it have a different probability than if it went a different way. I'll show it in a little while. To calculate dependent probability, we have to consider how the outcome of the first event will change the probability of the next event. So, first, let's brainstorm. some examples of dependent probability. And to start us off, think about how about drawing, taking balls out of a jar. The reason why this would be dependent probability would be because every time you take out remove a ball from a jar, there's fewer total balls. So in fact, you can't just multiply it out because you have to actually consider how many balls are in the jar now and like how has it changed. So ranging a certain
Ranging is
amount,
small.
maybe.
Yeah, like possibly, yes. A deck of cards, yes.
Yes, absolutely. Deck of cards.
Well, I just want to reiterate because without replacement is so big on math competitions, not just the AMC, it's big on the AMC and a lot of other math competitions. So without replacement means you're not putting something back, right? So if I have like five cards and I draw one, and let's say 3 red and 2 black, right? If I draw one, right? If I draw one and it's red, right? If I draw one and it's red, then I would have 2 red left over, right? That would affect the probability. So if the probability I draw a red one on the first attempt is 3/5, right? But since I drew the red one already, the probability that I draw a red one again is 1/2. So with replacement, it's 3/5, but without replacement, it's 1/2. So do you guys understand this replacement, this concept? It's not really a concept, but this like idea of replacement and like how that works and how that affects the probability. Yes, okay, that's good.
Okay. All right, I think we can go look at an example to see how exactly dependent probability works. So Jerry draws 3 lottery balls from a cauldron containing 10 balls, and he draws these 3 balls without replacement, which again, it means he doesn't put the balls back after he draws them out. And in this cauldron, there are 5 red balls and 5 blue balls. So what is the probability that all 3 of the balls he draws are blue? And let me just clarify something. In independent probability, we multiplied the probabilities together. In dependent probability, you can still do that. It's just you need to be careful about like how one event has affected the next event's probability. Okay, so anyone have an answer? Maybe? Okay, let's see.
12 over 90.
Okay. Hold on.
Okay.
Yeah.
So we can look at this, right? So let's go over this through every single draw, okay?
Okay,
So
wait,
it's
hold on.
with-
Let me draw some balls. Or shoot, that sounded weird. Okay, here is, I'm sorry, 3, 4, 5 red balls.
Oh, okay, yeah, I was kind of confused. I was like, because draw balls.
4,
Okay.
5. There. Okay, so we have the lottery balls, right? And so in the first draw, the probability that Jerry draws a red ball is okay, yeah, blue ball, sorry, blue ball is 5 over 10 or 1/2. So I'm just gonna write 1/2 because simplifying is a good idea. Okay, and after he draws
Amy,
this,
can you use a different color other than green? A little
Okay.
hard.
all right, let's
Mm.
see, 1/2. There we go. Okay, so once he draws one of the blue balls, it doesn't matter which ball he draws out, that ball is gone. It doesn't come back because it's without replacement. So next, he has to draw his second ball. And again, we want him to draw a blue ball. So let's say he draws this ball. It doesn't matter which ball he drew. And that probability would be 4/9. And the reason being that because he took out a ball from the cauldron last time, there are now only 4 blue balls left. And in total, there's only 9 balls. So it would be times 4 over 9. And
Wait, for
again,
the last one, does anybody want to like see, like, does anybody want to like put in or pitch in the last number, the last fraction that you would use?
It'd be
3/8. Yeah,
3/8.
that's exactly right. Because there's only 3 blue balls and 8 total balls. And then we can just simplify all that to get, let's see. Yeah, it's 1 over 12. I believe it's 1 over 12 when we simplify everything. Why don't we do the same for 1/2? Wait, sorry?
oh, we did do the same for 1/2. I just simplified it. So this should actually be 5/10. It's just I simplified it to 1/2. So yeah, sorry if that confused you.
Okay, so it looks like, does everybody understand that? Because this is something that you probably see quite often in some tests. So yes, okay, that's good. That's good. It's good that we understand that. So I think we can move on.
Okay. Sorry.
So two cards are drawn from a deck of cards, one after the other without replacement. Without replacement. So that without replacement is important. What is the probability that exactly one ace is drawn? Yes, so yeah, a note deck of cards has 52 cards and 4 of the cards are aces. So remember that. Remember that. That's quite important. This is actually a little harder because it's not both aces are drawn, right? Okay, Vishwa got 50/2650. My laptop, okay. So it looks like we're getting, I think I got 1/221. Okay, so it looks like we're getting different answers, right? So, well, who's, oh, okay. Yeah, so it looks like we're getting different answers. So we can just do this together.
Yeah,
So
so the question says that exactly one ace is drawn. One ace, not two, but one ace. So that, how many ways could you draw one ace? Well, you could have an ace in the first one and no ace in the second draw, or you could have no ace in the first draw and an ace in the second draw. So you do need to you may need to calculate the probabilities for both of those draws in order to find the total probability.
yeah, so
Oh, sorry, do you want to explain now or?
yeah, it's fine. You can explain it, but yeah, go ahead.
Okay. Again, as I just said, there are two ways you can do this. You can have an ace drawn in the first draw, but no ace in the second draw, or you could have no ace in the first draw, but an ace in the second draw. So we have to look at these individually because they're probably, well, actually, we don't have to look at them individually, but for the sake of like explaining this, I'm going to look at these individually. So first, let's look at if an ace is not drawn first, and then in the second draw it is. So the probability that an ace is not drawn first has a probability of 48/52. This is because, again, there are 4 aces in a deck of cards, and so that means there are 48 cards that aren't aces. So the probability would be 48/52, which I simplified to 12/13 because it's easier to work with. Then if you draw a second card after, the probability that an ace is drawn is 4/51. This is because there are 4 aces still in the deck, but we just drew a card out. So there would only be 51 cards actually left in the deck. So then, just like an independent probability, we multiply these probabilities together, 12/13 times 4/51, to get 16/221. I hope that's right. Then we have to look at the other possibility. If an ace is drawn first, then it would have a probability of being drawn. Oh, looks like someone has a question. I first did that an ace is drawn and then the non-ace is drawn. That would affect your answer if you don't do the other possibility, because what if the non-ace card is drawn first and then the ace card? Both of those have probabilities.
You have to consider both of the cases.
Yeah.
You need to be able to consider both cases. You need to do that.
Yeah. So you're halfway there. So the probability that an ace is drawn first has a probability of 4/52, which is 1/13. However, now since there's only 3 aces left in a deck, the probability of not drawing the ace would be 48/51, which again, we need to multiply this number and this number to get 16/221. And now we have these two probabilities. I'm going to circle them because there's a lot of words. There's a probability here, probability here. This first one is for if you get an ace and then some other card. I don't know what to write for that. Okay, first one is for if you get an ace and then some other card, but the second one is for the opposite case. So now what we have to do is we have to actually add them up. The reason why we have to add them up is because not multiply, don't multiply these together. We have to add them up because these, if you think about it, these are sort of like parallel events. They're both going through two draws. However, they're not like intrinsically like, they're not like independent events. They're actually, you could think about it like different versions of the same event. So we would actually have to add them together to get the total probability. We also have a question.
Yeah, basically those are both different cases, right? So if we multiply together, we're trying to find out like the probability of both of those happening. But those events are basically the same events. They're just two different parts of the same event. So they're sub events. They're kind of sub events. So instead of multiplying them together, we add them up to get the entire event. So we're kind of dividing the problem.
Yeah, also I have a question. So one person is asking how I got the 48 from 48 over 52 up here. So remember that there's 4 aces in a deck. So 4 aces, and there's a total of 52 cards. So if we want all the cards that aren't aces, we just do 52 minus 4, and that would give us 48 cards that aren't aces.
Looks like we have a question. Oh,
Yes.
so in certain cases, if we have 2 parts of the same event, we have to add, is that like a rule? So
Exactly, yeah. I mean, I guess it's not exactly.
it's not a rule, but you have to know. Okay, that's, I think, the hardest part about probability, in my opinion. Like when I first started out, it becomes much easier. Like as you do more probability questions, it's like determining when to add, when to multiply, and that's just something that you get like familiar with as you continue to do probability questions, because it just becomes like another like sense. Like you can kind of piece it out like using logic and just the problem itself. It's so like you said, right? If we have 2 different cases of the same event, we're not trying to find like the probability of both of those happening, right? Because we can consider them to some extent the same events. We're just dividing that same event into 2 different scenarios. So how that event happens. So we're not going to multiply the probabilities of like an event, like how it happens. We're going to multiply the total possibilities of like the total event. So what I'm saying probably sounds really confusing, but essentially
I have an
we're not gonna
analogy. I have
Okay,
an
go for it.
analogy if you think about it. So I don't know if you know about time travel or what, but let's think about it like this. You could think about like this is going to be like a timeline, right? This is going to be the first draw, and this is going to be the second draw of the cards, right? So if you're just doing normal independent probability without any weird adding up, you just multiply these 2 events together. However, the way we did this, we actually considered 2 possibilities. Is that if we draw something that isn't an ace and then an ace. And we also considered what would happen if we did draw an ace, but then didn't draw an ace. Technically, if you think about it, you could think about these 2 events occurring on different timelines because they're just different instances of the same event. So when you have like 2 different versions of the same event, then when you reach the end and you want to get the total probability, you add them up. I don't know if that helps, but I hope it does. So, yeah. Okay. Yeah, I don't know. This is just how I think about it. All right. Let's, if you guys don't have any other questions, we can move on. So.
Yeah, so we can move on to the next slide.
All right. So basically we have to add these probabilities to get the total probability. So yeah. Oops. The drawings are still there.
Those annotations.
Okay. All right, let's do some practice
problems.
problems. Oh yeah, so you can do this slide.
Yeah, let's just do some practice problems. Just put your answers in chat. I'll give you guys like a couple of minutes. We don't want to take too long since we have a couple other activities and um, concepts planned out. So probably we're gonna have to do this a little fast, but
Yeah.
okay, so different answers. Okay, so I'm gonna explain this really quickly, right? So let's think about this. What is the probability that two blue marbles are pulled out? All right, so the first blue marble happens with a probability of 2/7. So everybody agrees with that, right? Everybody, I just want everybody to say yes or no in chat. I need to know if you guys agree with it. So 2/7, right? Yes, everybody agrees with that. So what is the probability? Okay, now remember, this is wait, Amy. I think you have to clarify whether that's with or without replacement. So
Oh.
that
You know what? Let's do without replacement. This is without
okay.
replacement.
Okay, so without replacement, right? So without replacement. So if it's without replacement, meaning we're not putting anything back, what is the probability that I get a blue marble on the second attempt? 1/6, exactly, because there's one blue marble left and there are 6 total marbles. So what is the total probability once you multiply everything out? 1/21, exactly, that's our answer. So does everybody understand how we did that? Yes, okay, that's great. Let's move on to the second problem.
Yeah, we gotta hurry because we have another
Yeah, we do.
topic.
So same thing. You guys can read this. Same kind of scenario. Amy, let's do without replacement again.
Yeah, without replacement.
Okay, so
Any other answers? Yeah. Okay.
yeah, so it is 1/13. It is 1/13. So let's look at this, right? The probability that I get one red marble is 4/13 on the first attempt, right? So 4/13. And then now the second attempt. What is it going to be the second attempt? Somebody in chat, just tell me. 3/12, exactly, because one red marble is gone and there are only 12 left. So once we multiply everything out, we're gonna get 1/13, exactly. So that's how we get 1/13. So let's move on to the last problem. What is the probability of pulling 2 spades from a deck of 52 cards, 1/4? Okay, wait. So this problem is a little vague because we don't really know how many cards we're pulling out. So how many cards will we be pulling out of the deck?
2 cards.
Okay, so we're pulling out 2 cards from the deck, right?
Yep.
Okay, without replacement?
Yeah.
Okay, without replacement. So look, so the probability that I get, okay, so we know that 1/4 of the cards are spades, right? Because there are 4 suites. I said suits. There are 4 suits in a deck of cards. Uh, so the probability that I get a spade on my first attempt is what? What's the probability I get a spade on my first draw? 1/4, exactly. So 1/4. Amy, do you want to?
Sure.
Now, what's the probability that I get a spade on my second draw? So remember, if 1/4 are spades, okay. Yep, exactly. So it's 12/51, right? Because there are 12 spades left and there are 51 cards left. So 12/51. So once we simplify that, we get what? Yeah. So once we simplify that, we get 3/51, which simplifies to 1/17. So that's our answer. So I hope we got all those right because I didn't check the answers.
Okay.
1/21, 1/13. Yep. So it looks like we got all of them right.
Yep, that's nice.
Looks like we got all of them right. So that's perfect, you guys. Okay. So we are what? 1 hour and 30 minutes into class time, around 1 hour
Yeah.
and 30 minutes. So we're just gonna take a quick 5-minute break. So you guys can do whatever you want for 5 minutes and we'll see you again. in a couple
Yeah.
minutes.
Go to the bathroom maybe or something. Yeah. Yes, class ends at 11:30. Yeah, Sai, I know. Yep, 30 minutes left.
All right, everyone, our break is actually over, so we're gonna continue with our lesson.
Yeah,
So welcome
okay.
back. We hope you had a good 5 minutes. We're gonna move on to a new concept. It's called casework, and
This
I think a
concept is
lot of you
actually
guys
pretty
know.
fun. I like
Yeah,
casework.
casework. I love casework. I love casework. Yeah, it's fun. It is fun
Yeah,
when you
so
have all the cases.
yeah. All right. Hopefully everyone is alive. And if you are alive, put a message in the chat. That way we know you're
Yeah, tell
here.
us your case. Tell us your case of aliveness.
Yeah.
I'm here. Hello. That's great. So everybody's
Okay.
here. So I think we can just continue onwards.
All right. Sai, you can do this.
All right. So casework is basically where we solve a problem case by case, and we basically like simplify the problem, and it leads us to a solution in a much more elegant manner. So it's
Yeah.
kind of cool when you have all the cases. It's actually really fun. So we can work on some examples.
All right. So how many numbers can be made only with the digits 1, 2, and 3, where each digit can only be used once? And so now here's the thing. No, you're okay, Advika, you are on the right track. However, you forgot some numbers. There are actually, I think you are thinking of 3-digit numbers. However, the question didn't say that it just had to include 3-digit numbers. So yeah,
That's fine.
you're on the
Okay.
right track though. So
You
yeah,
guys are on the right track. So
yeah,
okay, so remember what I said earlier, right? Casework. So we would have to split this problem into cases. So before you even pick up your pencils, just think about this. What cases would we split this up into? Like somebody just tell me in the chat if you can.
if you don't know what cases means, think about like splitting the problem into smaller problems or categories. So in this case, what are the different types of numbers?
1 digit exactly. Okay, that's exactly it.
Yes.
So Vishwa had all the proper cases. So case 1 is where the number is 1 digit. Case 2 is where the number is 2 digits, and case 3 is where the number is 3 digits. So you see how that helps us solve the problem, right? Because now we have these smaller problems which we can pretty easily solve. So if the number is 1 digit, how many possible values do we have? 3, exactly. Number is 2 digits, how many possible values do we have? 6, exactly. And the number is 3 digits, how many possible values do we have? 6, exactly. So adding all these up, how many values do we have? 15, exactly. You guys really went through that problem really well. That's really good. I'm actually pleasantly surprised that everybody was able to do that. So yeah, that's great. And this was also a lot of people's first casework problems. That's really nice. So remember how we get these values, right? So if the number is 2 digits, remember I have 3 values, and remember each number can only be used at most once. So if it's a 2-digit number, at most, I can put 3 numbers for the first digit and 2 numbers for the second digit, right? So that's 6. Now for the third, for case 3 digits, right? At most, I have 3 digits for the first number, 2 digits for the second number, and 1 digit for the last number. So it's 3, 6, and 6. So when we add all these up, we get 3 plus 6, which is equal to 15 values. So 3 plus 6 plus 6. Everybody understands that, right? So now we can move on to the second case.
Yeah, casework can also be
Wait,
used.
wait. Before
Oh
we
wait.
continue on, are there any questions? Just really quick.
Oh yeah, questions are important.
No questions? Then we can move on. Let's go. Amy.
All right. So here's the thing. Okay. Casework can also be used in other more I guess visual problems. Oh, we have a question. All
I
right.
didn't understand. All right. Amy, do you want to do that
All
again?
right. I'll re-explain. So if we're looking for how many numbers can be made with the digits 1, 2, and 3, and it doesn't matter how many digits make up the number. So if we want to make the problem easier to solve, we can split the problem up into cases. In other words, we can first solve for how many 1-digit numbers there are, and then we can solve for how many 2-digit numbers we can make, and then we can solve for how many 3-digit numbers we can make. And for each of these, we can look in for each of these, we can solve, and then once we get the number of numbers for each case, we can add them up to find the total answer. So, like, for example, for the first case where the number is just one digit, we have three possible numbers we can make. 1, 2, and 3. Those are the numbers. So then for case 2, we have 6 possible values because again, going back to our little fundamental counting principle thing, for the first digit, hold on. For some reason, I can't draw anymore. Okay, there we go. For the first digit, we'll have 3 possible values because obviously we have 3 digits. But for the second digit, we have 2 more possible values for what digit it can be because we can't use the digit that we've already used before. And so that would give us 6 different values. So yeah. And then finally for the third case, similarly, we have 3 digits. And for the first digit, we have 3 possible values, 1, 2, or 3. For the second digits, we only have 2 possible values because we already used one of the digits. And for the third value, we have only 1 digit because we already used all the other ones. And so that gives us 6 possible numbers. So once we add these up, we get our total of 15 possible numbers that can be made with the digits 1, 2, and 3. Okay, so any other questions?
Well, do you understand Emmy's explanation? Whoever asked the question, what is it? Harsh. Well, I think we should just move on. Okay, I got it. That's great.
Okay,
All right,
that's great.
we can move on.
All right, so we can also use casework in other situations. So for example, how many triangles are in this diagram? And let me just point out that there are other triangles than these little guys.
Yeah, there are other triangles. And
Like-
the only way we could really efficiently calculate for that would just be casework, right? Because there are different, like, shapes and sizes, and like, if we can just like categorize these different kinds of triangles, it'd be way easier to solve, right? So does anybody have any idea on how we could do that? Because like here's a hint, like the shape of the triangles, like there's their size. So 1 by 1 triangles, or 2 by 2, or 3 by 3, and by that I mean the side length. So 1 by 1 would just be
Big,
Oh, yeah.
medium, small?
kind of big, medium,
Maybe.
small, like on the same track. So this is what I'm thinking, right? So 1 by 1. So those small little triangles, we can call them 1 by 1s because well, not 1 by 1s. Let's just call them side length 1s, right? Because these are all equilateral triangles, so their side length is just going to be 1. So side length 1 would be in one case. So what would be another case, guys? So we know that side length 1 is one case. So what would be another case? Exactly.
2,
Side length
yeah.
2 would be another case. So what would be another case? 3, exactly. So what would be another case? 4, exactly. So what would be do we have any more cases? No, exactly, because our side length 4 triangle is the largest triangle. So now that we have 4 cases, we can just individually solve for the total amount of triangles in each case, and then we just add them together. So we basically break down this problem into this casework manner, and it just becomes way easier to solve. So
All
let's
right.
just do it.
Yeah.
Amy,
So wait. So now guys, let's approach this case by case. So first, how many 1 by 1 triangles are there in this diagram? Yeah, 16 of these. Pretty sure, yes. 16. Now, how many of these 2 by 2 triangles are there?
Well,
You guys are close.
It's
Very close.
actually very close.
Just don't forget
It's
this one.
actually 7. You guys forgot the bottom upside down triangle there. So it's 7 actually. 7. You guys were really close. There's an upside down triangle that you guys might have forgot to consider.
Yeah.
So it actually makes it 7. Okay.
Okay, next, how many of the 3 by 3 triangles are there?
Well, you're close. Yes, so it's actually 3, guys.
Yeah, there are 3 of these
3.
triangles, which I'm going to draw on the screen. Okay, now how many of the 4 by 4s are there?
This is the hardest one. I mean, the easiest one, sorry. Yeah, 1. So yeah, that's the easiest, right? Because there's just one large triangle. So adding everything together, what do we get?
And if you forgot the numbers, I'm going to type them in the chat. Yeah, I think, pretty sure.
Yeah. So good job. Yeah. So when you add everything up, you're gonna get 27, and that's basically. So do you guys see? Do you guys see how much easier that problem was? Like, imagine just attacking this problem brutally, right? It's gonna be so much harder because you're gonna have to you're gonna just you just have to randomly count, and you wouldn't know. Have I already counted this? Like, do I have to go back and count it? It's gonna be so much more confusing. But casework really makes everything so much easier.
Also,
Like,
I have a question. I think someone would like me to explain it again. So I'll quickly go over it again. So basically it's asking how many triangles are in this image. However, there's a lot of different triangles of different sizes. So for example, you have these little ones right here, and then you have this big one. And basically what we're doing is that we're splitting the triangles into categories. So like these little triangles, and then these 2x2 triangles, and then these 3x3 triangles, and 4x4 triangles. And we're going through each category and counting how many triangles are just in that category. And once we have all the numbers, so we see there's 16 little triangles, 3 of these 3x3 triangles, 7 of the 2x2 triangles, and 1 of the big 4x4 triangles, we can add these up to find how many total triangles are in this diagram. Okay, now, oh shoot. Okay, we are going to skip this problem quickly because we may not have enough time. However, I'm just going to still quickly show it. Question is, how many different squares can you make by connecting 4 of the dots on the grid? Basically, there's different types of squares, which you can see here, including these tilted squares. So yeah, we're skipping it because we're kind of running out of time.
yeah, we're
So
kind of running out of time, guys. But yeah, that's a brilliant problem. And
I'm also going to skip this one because it's kind of running out of time. All right. So now you guys should try this problem. How many triangles are in this figure? Again, triangles.
and try this by yourself before we do this. And remember, casework is probably what you should do. You're gonna solve this problem. Be efficient. Just wait one more minute before we go through this, since we're just a little short on time. So we're just gonna wait just a minute or two more. 20.
Oh, yeah.
Wow. Okay, that's actually
yeah.
correct. Good job.
Yeah, that's correct.
That's good job. All right, that's
Yeah,
a really
that's
nice job.
great.
Good job. Well done. Well done. All right. So, do you want to explain that to us? Who gave us the answer? Advika, do
Advika.
you want to explain how you got that?
So first, I did the individual triangles.
Okay, Amy,
So I
put down case 1. Oh yeah.
Yeah.
sure.
Yeah, I said that there are 12. Then I did the 2x2 triangles. So in the straightforward triangle, there's 1. And then when you look at the tilted triangle, the upside down one,
Mhm.
you can see that it makes 4 other.
Mhm.
And then completely the upside down one would give us another. So you get 6 in that total.
Yeah, I was actually concerned that some of you guys might not count the upside down triangles, but yeah, that's a really good job. Yeah, good job on catching those upside down
And then for
triangles.
the 3x3 ones, there's only 2.
Mhm. Yeah, that's
And then
cool.
I added it up.
All right, that's great. Yeah, that's exactly what you're supposed to do. So we have 3 different cases. I'm getting 8 2x2. Okay, yeah. So for the 2x2s, actually, Amy, you want to draw those out?
Yeah, I can
So
draw them
we would
out.
actually get
The way I
3.
thought of looking for the 2x2s is that each 2x2 can actually only fit on one of the little pointy thingies of the little star. So we have 1 2x2 here. We have 1 2x2 here. We have 1 2x2 here. Another one here. Here again.
Can I say something?
Sure.
Yeah, go ahead.
Actually, 3x3s.
Oh, there are? Where?
Yeah. I'll show you. So the first one is this one.
This one?
Yeah,
Okay.
that's the first one.
Yep.
and then the second one is this one.
Which one?
Oh, wait, never mind. Actually,
That's
Yeah,
fine.
that's all
That's
right.
fine. Thank you. Thank you. No, thank you for at least trying. Because I actually thought maybe for a second you were right. Because
Yeah.
I don't know. Maybe there's something in the middle I couldn't see, but it's
Yeah.
fine. Yeah, so there's actually six 2x2s though, right? Because the way I thought of it and the way Amy thought of it was pretty smart. But the way I thought of it was that I saw that there was three, like you could just fit three in like the top one. So I see two different 3x3 triangles, right? So I see those two triangles and I see that I can fit three in each one, right? So the bottom row I can fit two. Yeah, I just take one and then I realized that I can fit two in the bottom row and one in the top row. So yeah, and then one is up. So that'd be three. And then I realized that the bottom triangle is the exact same thing. So I know that there's by symmetry, there's just going to be another three. So it's just going to be six. That's how I did it. There are different ways to do it, obviously, but yeah. And the important thing is that we get like the total number at the end of the case. So that's good. So it's good that we got that answer. What's 20? Yes, thank you. Thank you. I think we're done with that one.
Do you want
Alright.
to do this one or no?
We should probably just skip. Do you think the progress check is necessary? I think we might. Let me just check how long that'll take.
Yeah, you should check which ones we should do because
Mm,
oh yeah. Hmm.
hmm.
I mean after
Okay,
this is
okay. I think this is what we'll do. Here, Amy, I think this is what we'll do. We're gonna skip number one. We're gonna do slide 4, slide 5.
wait, which one?
We're gonna do slide 4, 5. Well, there's only 3 though. Okay, we're gonna do slide 2.
For what? The Jamboard?
Oh, the progress check. The progress check.
Oh, I'll skip to the progress check.
2. We'll do 2, 3, and 4. We'll do 2, 3, and 4. So
All
everybody
right.
go to the progress check and we'll do questions number 2. Oh, 13. Okay, 2, 3, and 4. Okay, so
All right.
questions numbers 2, 3, and 4. So we're gonna do questions 2, 3, and 4, and we would almost be done by then, and everybody would be free to go. So
Yeah.
everybody do this first on your own, and then we'll do it together as a group. And I think this problem is really easy, so everybody should be able to do it. Oh, is somebody drawing on it? Wait, has anybody done 2? Yeah, can you guys put your answers in chat? Because
We're on the Jamboard.
yeah, we're on
Am
the
I-
Jamboard.
Yeah.
Yeah, 2 is really easy. I think everybody here should be able to do 2, right?
Wait, can you guys edit the Jamboard or no?
We can edit it.
Okay.
Okay, that's good.
Once you guys
Okay,
get the
then.
answer, you can write
What'd you guys
it. You
get?
can. Yeah, it looks like someone put 21 on
21.
there.
So this is fairly easy. I think everybody knows how to do this, right? So it's just 7 times 3, fundamental counting principles. So 21. Okay, we can move on maybe to 3.
Okay. Calculate the number of 4-digit integers whose thousandths place is a multiple of 3. And to help you guys out, I'm going to draw a diagram. These blanks are just going to represent where the digits can go.
And remember, we can actually split this up into cases. So that's something. If you guys needed. Yeah.
Oh, I see.
Yeah, exactly. So we got a right answer. Shayan, good job. So remember, we can split this up into 3 cases, right? The first case would be that the first digit is 3. The second case would be this, the first digit would be 6. And then the third case would be the first digit is 9, right? Because we know that the first digit has to be a multiple of 3. And there are only 3 multiples of 3, right? That are like, that the first digit can possibly be. So that'd be 3, 6, and 9. So each each one of those cases would have 1,000 possibilities because the other three digits in the 4-digit number have 10 possibilities each. So it'd be 1,000 possibilities for all three of the cases. So we'd get 3 times 1,000 is equal to 3,000. So I can answer in the chat. Yes, you can, Vika. Yeah, that's totally fine. So 3,000 cases. Do you guys understand how we got 3,000? Any questions on how we got 3,000? Are there any questions on how we got 3,000? Because if there aren't, if there are no questions, you can just say no questions in the chat. So I understand that nobody has questions. No questions. All right. So it looks like nobody has questions. So we can just move on. This is going to be our last problem before we just go over the homework. You think we can go over one more, Amy?
Yeah, I have it
Okay,
on.
we can go over one more after this one.
Okay. So how many parallelograms are in this image? And you guys can draw on it if you want. Like this is a Jamboard. You can basically do
Yeah, it's just
whatever
a
as long as you're
Jamboard,
not
yeah.
just wrecking around.
Yeah. So remember cases again. $13. Somebody got 13. Okay.
I see someone else also got 9.
Yeah, I got 9 as well. I don't have the answer accessible to me, but I
I
also
believe
got
it's 9.
Yeah, I
And
also believe it's 9. So we would split this up into 3 cases, right? So the first case would just be 1 parallelogram. The second case would be 2 parallelograms, and the third case would be 4 parallelograms, because we can't make a parallelogram out of 3 parallelograms in the figure. So 3 cases. So there are 4 individual parallelograms, and if we connect 2 parallelograms, we get 4 more. So I can actually edit the Jamboard. So here, I'm gonna edit this. So this would be 1. This would be another. This would be the third, and this would be the fourth. So those are the 4 different parallelograms that consist of 2 individual parallelograms, and then the last one is just the big parallelogram, right? So, and remember, we can't make a parallelogram out of 3. Like we can't do this, right? Because that's not a parallelogram. So you get 9. All right, good job, Tanisha. Good job, Charlie. Good job, guys. So the answer is 9, and we have time for one more problem, and then we'll just go to the homework, and we should be done for today.
yeah, so how many total rectangles of any size are in the following image? And yeah, there's 3 examples of different sizes on the image of different colors. So yeah.
Remember cases here.
So squares count, right?
Yes.
Yes, squares are rectangles. Okay, so this one's gonna be a little bit harder, and I'm just gonna go over this because we don't have too much time left. So I'm just gonna be going over this really quickly, and then we should be done, guys. So case 1, what's the first case? Somebody tell me. What's case 1? Wait, I think I typed. Is it not showing up on the Jamboard? All
No,
right.
there's a bit of a delay.
Okay, it's fine. No, it's because I didn't finish my thing yet. So the first case, let me just write this up completely for you guys. So case 1, case 2, case 3. I don't know how many cases there are, so I'm just gonna put a lot of cases, and we don't even have to use our cases. So, right. So look, the first case, right, is that there are individual, just one by one, right? Individual. So how many of those are there? Well, we know there's 4, 8, 12. So there's 12, right? So I'm just gonna draw 12 here. 12. First case. Now for the second case, what we're gonna do is just utilize 2 squares. So how many rectangles can we form using 2 squares, right? So that'd be 1 here, 2 here, 3 here. So 3 per row, and then per column, 1 here, 2 here. So 3 per row, 2 per column. So let me just write this. So 3 per row would be 12, and then 2 per column would be 8. So we get 20. for the second case. Amy, is that right? 20 for the second case, right? Because 3 per row. and two-
Um, wait, wouldn't it be 9 and then plus the columns?
No, because
9
look,
plus 8.
9, wait, 3, wait,
There'd be
2,
9 of the
wait, 9, oh, yeah, my bad,
horizontal,
9.
9
9,
of these,
So 17, my bad. I actually had 17 on my paper. I don't know why.
and up here. So
17,
you would
yeah,
have,
17. It'd be 17. If I'm not wrong, it'd be 17.
yeah, I believe it's 17.
Yes, so it
Yes,
is
it-
actually 17. 3, 9, and then wait. So 8. So 17, right? And then the third case is using 3 rectangles. So that'd be 1, 2 per row. So it'd be a total of 6 and then 1 per column. So it'd be 10, right?
Yes.
Okay, and then the fourth case would be 4.
Wait,
So that
did
would
you say
be-
3 rectangles or 4?
No, 3 squares. We use 3 squares to form a rectangle.
Or wait, wouldn't that be just 6? Or
No,
oh
it'd be just
shoot,
the columns.
vertical. I forgot
Oh, Arya,
vertical.
can you like adjust the size of your post-it note? It's a little big. Can you adjust the size? Like, can you like make it smaller or because it's kind of obstructing the view.
Oh my gosh.
Okay, it's fine. Okay,
Yeah.
thank you. Thank you. So
Yeah,
now
there
we're
are-
gonna use now we're gonna do 4. Now we're gonna be doing 4 squares. So that'd be 1 per row. So 3, and then now we're gonna
Plus
consider
1, 2, 3, 4,
and now
5,
we're gonna be
6.
considering like the squares. So 2, 3, 4, 5, 6. All right. So does
So in
everybody see
total.
that? So it'd be 6, like the 2 by 2 squares, and it'd be like 3 rectangles. So it'd be 9. So we would have 9 for that one.
Yes. And you can't
Now for-
actually make any rectangles with 5 squares
5, yeah. we
because
can't
then
make
you
it-
would make something weird like this. So we can just skip that case because it doesn't have anything.
And now we can do 6 squares. So that'd be what? I got what? 1, 2, 3.
1, 2,
3.
3,
So I got
4,
7.
5, 6, 7. There are 7
3,
rectangles that are composed of
got 7
6.
as well. So 1, 2, 3, 4, 5. Yeah, I also got 7, which is good. We got 7 with 6, right? Now we can't do 7 squares, but we can do 8 squares. So that would just be our 3 by 3s, right? And our 2 by 4s. So that would be 1, 2. So we only have 2 for those
The
2 by
8s.
4s. The 8s, we have 2 for the 2 by 4s though. And then we have for the actual thing squares, we have 2. So we have 4 for those, right? Because I'm going to show you guys. So we have these big squares. There are 2 of those, and then we have the 2 by 4 rectangles. Those would be these. That'd be 4.
3 by 3 squares are made of 9 squares, Sai.
Oh my god. Oh wow. Yes. Okay. Looks like I messed something up. But no. Okay. Yep,
No, it's
that
fine.
did not-
It's fine.
That's-
It's you're still basically
Plus
there
2,
are
plus
2 that are made up of 8, and then there's 2 made up of 9. And finally, we have
and
one
we
that
can't have
is
any
made
more
up of
10 or
12.
11. Yes. So you guys see that? There's no way we could have solved this problem. There's absolutely no way that we could have solved this problem without casework. Well, we could have, but it would have taken a lot of time, and it would have been very messy. So now we're gonna calculate everything, and we get what, 29.
60. We get 60 in total. In total, there are 60 rectangles. And I know that took a while. It took a couple of minutes to write all of those out, but casework is better than just randomly, I don't know, circling rectangles and stuff. So yeah, okay. Sai?
Before we conclude this, anybody have any questions, especially about this problem, because I know it might be a little confusing. But essentially, what we did is we split this up into cases, and we use like these different squares. We use these squares as the building blocks for all our cases. This would be 1 square. This would be 2 squares. This would be 3, 4, 5. So you guys understand how we did that? So this basically, these squares were the building blocks for our casework. And with that, we were able to get the answer in an actually decent amount of time. So
Okay.
good job, everybody. I think we're done. So
Yeah, we have to just go over one more thing, and it's
yeah,
about
homework.
homework. Homework in this case is not really, well, yeah, we didn't get to that. Okay.
We can get to the breakout room activity, but it's
Okay.
okay.
Yeah, basically
Oh, wait.
what homework is just going to be is 5 questions. Obviously, it's summer and you guys are in math class, and we don't want to give you too much because, yeah. So it's just going to be 5 questions reviewing what we taught you in class today. They're basically in this doc. They're also going to be posted into the Google Classroom. You guys can print it out because I think that would help you. I prefer, personally, at least for me, I prefer writing stuff so you guys can print it out. If you don't want to print it out, you can make a copy of it.
Mhm.
You won't exactly be turning it in necessarily,
so you
but
won't be
we
turning it.
will be going over it in class and we can answer your questions and we'll be calling on you to, help explain the questions. So,
Yeah.
yeah.
We won't be going over it. We will be going over it in class, but we won't be making you turn it in. If it's not like something that, if it's something that you absolutely can't do, then it's fine. You don't. But we just encourage that you do it so we can test for your understanding, so you know how much you understand the concept, and you know if you have any questions, you know what to ask us, how to do something. And Tanisha, your hand is raised. Do you have a question?
Yeah, so do we like make a copy and then we like don't turn it in? If I'm
mean,
Yeah,
right?
you don't have to turn it in, but we do encourage that you do it. Like we highly, highly encourage that you actually do the homework.
Yeah, you can
But you
make a
don't turn it
copy
in.
of it, or if you would like to print it out, you can also print it. So,
You can print it, or you can just look at it. You can just do it in your notebook. You can just write down your answers, do your work in your notebook. You don't even have to make a copy, really.
yeah.
And with that, are there any questions? Does anybody have any questions? Amy, do you want to?
I mean, if you guys, yeah, I mean, I guess we're pretty much done today. If you have any more questions, you can stick around and we'll try to answer them. If you think this lesson was awesome and you really want to come tomorrow and you want to get a head start on tomorrow's lesson, we're going to be posting this slideshow so you can take a look at that.
Yeah, we're gonna be posting the slideshows in the Google stream, and yeah,
Yeah.
I think that's it. Amy, do you want to move to the question slide?
Oh yeah, the epic
Yeah,
question.
Amy worked
Oh
really hard
shoot,
on this
sorry.
question slide, guys.
Yeah, this is a slide I
Sure,
worked the
make sure you
hardest
show
on.
hardest.
Yes.
See that? Those multiple images. Yeah, so with that, are there any questions? Thank you guys for attending to this class, and we hope you guys learned at least something.
Yeah. Oh, and by the way, if you think this class is too easy or something, we're going to be picking up speed in the next few days. We're going to be getting into more hard concepts. Tomorrow, we're going to be learning about factorials and permutations and combinations. Don't be scared by those words because we'll be teaching them
You'll
tomorrow.
be fine.
Yeah.
And we're gonna go over like more word problems, like casework, complementary counting, which is personally something that I really like to do.
Yeah.
We have a lot more advanced problems, and if you think that this is a little too hard for you, then you're welcome to
Ask questions.
ask questions. Yeah, ask questions and find out what you need to know.
Yeah.
And we hope you guys had a great time, and
Yeah. So
hope you guys learned something. So
yeah. See
we're
you
done for
guys
today.
tomorrow.
See you guys tomorrow. Thank you, Treyon, for attending today's class.
Yeah,
Thank you,
thank
everybody.
you.
Class.
Bye.
Bye. Bye, everybody.
Bye, thank you.
Yeah, thank you. If you have any questions, you're welcome to stick around. Thank you. Thanks. See you tomorrow. Yeah, we'll see you guys tomorrow. We hope everybody attends tomorrow's class. It's gonna pick up a lot more speed. So, Advika, do you have any questions? Deepika and Advika, do you guys have any questions? Or